Hello and welcome to my channel. This is Milosoft. In today's video, we're going to take a look at two games. The first one is Paws. Now, Paws uses location 1 to check if the tape drive is in use. And the idea is if you have a store-bought copy, the tape would shut off when the game was finished loading. If you copied it on a tape deck, then you might have a 45-minute or a 90-minute tape, and the tape drive would still be running when the game was finished. So what the publisher did was they checked to see if the tape drive was operational, and if so, it would crash. And we're just going to go over a quick look at the code. So location 1 is made up of 8 bytes. Like all of the locations on the 64, they're bytes. If you add them up, you get 255 because it's an 8-bit computer. You cannot have anything higher than 256 in memory. If you're basically just programming in machine code or BASIC and you're not doing a lot of math, you don't necessarily need to know how the bits work. But if you want to break down how each individual byte is comprised, then it would be a good idea to kind of learn your bits. So I'm going to put a screenshot up, location 1, and that we're looking at bit 4. Bit 4 would be 0, 1, 2, 3, 4, 16. We're looking for bit 16 of location 1. Now, I already have Paws loaded into memory. This is going to be kind of a quick video before we get into the main attraction. I'm going to assemble some opcodes here. And what I'm doing is I'm setting up different ways the game could be reading location 1. And these are the opcodes right here. And then we're going to do a hunt from 0800 to FFFF to see if there's a load X with 1. There is not. Is there a load Y with 1? There is not. Is there a load A with 1? There are. So this is ORing location 1 with 5. That's not what we're looking for. This is ANDing it. That's not what we're looking for. That's not what we're looking for. If you look at this code here, so this is the opcodes that we searched for. Load accumulator with 1. And this is exactly what we're looking for. It takes what's in location 1, puts it into A, and then ANDs it with $10, which is 16 in decimal, which is the bit we're looking for to see if the tape drive is on. And as you can see from the image, if the bit is 1, if it's on, the tape is off. And it goes down to 1, 3, C6, and exits. The tape drive is on. It goes in increments 8000 E. If it's not equal, it goes down to the exit routine. So what this is doing is it's acting like a car odometer. Is the tape drive on? Check location 1 and bit 16, not equal, exit. If the tape drive is on, increment 8000 E, so that becomes a 1. And then as time goes on, this continues to go up and up until it reaches 255, and then it rolls over and increments 8000 F. Comes 255. And that happens here. You increment 8000 E. If it's not equal to 0, go down here. If it wraps around to 0, increment 8000F right here. So basically we have a virtual odometer if your tape drive is on. Let's find out why. Hunt from 0800 FFFF for 8000E. We write it backwards, low bit first, high byte second. And there are two places. We already know of this one. And this is basically duplicating what the other routine does. Checking location 1. And bit 16. So 8000E is just incrementing. It's not doing anything in particular. What is 8000F doing? And here at 364B, we have an answer. So here's our odometer. It's incrementing because the tape drive is running. Load 8000F. There's no compare, so it's just going to see if it's equal to 0. If it is equal to 0, go down to 3654. Right here. Compare it to 6. Is it less than 6? Go down here and exit. So this routine here fires if 8000F is 0 or greater than 6. And what it's doing is it's checking, it's giving you a grace period. So you've loaded the game and your tape drive is on. It gives you until this increments up to 6. So that's a pretty generous amount of time. It's going to go 7, 8, 9, 10, and then it's going to up to 1, 2, 3, and then once it hits 6, it falls through to here. And why is it doing that? It goes to 15F1. 15F1 is a lot of arithmetic. Takes a number of E0, ANDs it with what's in 19B4, ORs it with 32 decimals, stores it back. And in the end, it just loads a single value and returns. So 15F1, I'm going to make a little routine, JSR. And you can see it's just, there's no pattern. It's truly random. Do you know what it's doing yet? Do you have any idea? So if the tape drive is off, nothing happens. If the tape drive is on, 8000E and F are going to increment. It's going to get a random number and put it into the accumulator, A, and store that in location 30. So let's say location 30 is a 34. It goes back and it calls another random number and puts it in 31. So let's say 31 is 22, just a random number. It goes back, gets another random number, and then stores it in 30. So let's say the number is 45. Now it's using indirect addressing, which means it's indirectly accessing the location. And the way that works is, here's our example. So it puts 34 into 30. It puts 22 into 31. And then it reads it indirectly. So it's actually reading 2234. It takes the low byte and the high byte. It's another way of saying store in 2234. But because we changed the value of 30 and 31, we're indirectly accessing it. So it's picking random numbers and putting random numbers in random locations. In essence, what it's doing is it's trashing memory. It is completely trashing memory. Now here is where the problem lies. Let's say that you have an original copy and your tape drive shut off. Okay, not an issue. And let's say that maybe, I don't know, you decided you want to rewind the tape or something after the game's done, so your tape drive is on momentarily. This is enough of a grace period that your tape should be done by then. But this here is completely wrong. 8000F is set to a 0. So the moment this routine is called, it goes down to 3654 and trashes memory. Just to put it to the test and kind of demonstrate what I'm talking about, we're going to set a breakpoint to 3661. So if this line gets executed that actually corrupts memory, we're going to know. I'm going to exit. I'm going to make sure my joystick is turned on. Run. Fire. And it has called the routine. So it's already started to corrupt memory. And the tape drive is off because 8000F is equal to 0. If they started it at 1, the way it should have been, it would increment. This would go up and this would wrap. But because it starts at 0, it's corrupting itself. So we're going to fix this. We're going to do a proper crack and make sure that this game works from now on. And to do that, we can just take this out, this store to 30. Just to go over it again, anything that's in brackets is indirect. So you're not writing to that actual location. You're using it as a pointer. You're taking what's in 30 and 31 and writing to those locations. So it's changing 30, 31 to whatever it wants and writing whatever it wants. We can remove that, but because it's an RTS, we can just move up. And right here's a good spot. At 364B, we're just going to put an RTS. So now when this routine is executed, it's just going to return back to where it was called from. This will never get touched. There's other things we could do. We could just take out the whole odometer altogether, but this is easier. Doesn't matter if the tape drive's on, if the tape drive's off. And because I have it loaded in memory already, it's not using screen memory. It starts at 0800 and goes all the way up to F1000. So it's basically using all of memory. Bank 0 will make sure that the kernel and basic are turned off so that we can save what's under it. If you're using the Vice emulator, what you could do is go over and put a 34 where location 1 is. And that will open up the RAM. If you see here, at A1000 and E1000, this is all game data. Normally this would be the kernel, but we've turned it off. So we're going to save data from 0800 to FFFF. That is done. We're going to open our command prompt. Now, I did attempt to make this video in 1920 resolution because a user on Lemon Fungus told me that the video seemed stretched. So I made a proper video in the proper resolution, but the playback was choppy. You couldn't see anything that I was doing. So unfortunately, given my CPU, you're going to have to deal with a smaller resolution. Go into the folder where my file is saved, data. Because I was using CCS, it put the data in the folder. And we're going to use Exomizer, which is a cruncher. We'll discuss that in another video. The format is Exomizer, SFX, start address. The start address for this game is 20993. So 5201. 0x5201, the input file name, the output file name, I already have it here, but it's going to overwrite it. You can see it's crunching from 0800 to FFFF. It's going to go through a couple different passes. I had this already because of the previous video that turned out choppy. So in total, this video has taken about 3 hours of my time. That's why I'm rushing through it. At this point, I just don't want to be bothered with it anymore. I just want to get it done so we can move on to the second half of the video. And we're finished. Let's do a hard reset. We'll go to device 8, go to our CCS folder, Paws crack. We should see something down here, which is Exomizer decompacking. And if all goes well, we will have a cracked game of Paws. Okay, looks good. Plays well. No glitches. And this is patched. There's no corruption occurring. So that will cover Paws. This was a little bit of a rushed video just because I've made it so many times. I just want to be done with the video. And we'll see you in part 2 coming up. Hello everybody, this is Milosoft, and in the continuation of this video we're going to look at Back to the Future by Electric Dreams. So I have the disc loaded into Durmaster, and we're going to take a look at the BAM, and we can see that this is a 40-track disc instead of the usual 35 tracks. Track 36 is all error 20s. So let's have a look and see what the game is like. It says SYS 4096, however the file is just 1 block long, so that is not going to be correct. What we have is hidden lines of BASIC here. So Polk 808, 234 disables run stop, sets the screen colors, and then it loads 1, and it loads 5. And here's the gameplay. So what I'm going to do is I'm going to make a copy of the disk, and just drag the files over so we don't get any of the protection. And we're going to save it as, we'll call it crack. And let's see what happens if we try to play the cracked version. So we can see some obvious disruption. The game is corrupted, very much so. So something did not work. Given that the game is using disk errors on track 36, what we're going to do is we are going to load the files one by one, and we're going to go into the monitor using Alt-M. If you're using Vice, you can use Alt-H, and we're going to check 2D and 2E, which is the bytes to the load address of the end of file. So this file ends at FF4, excuse me, FF40. And we're just going to check for some common drive commands. Hunt from 0800 to FFF, F for FFBA, FFCF. There's nothing there. We're going to go on to file 2. That is obviously color RAM. You can see the top of the screen has turned yellow. We're going to load 3. The end address is C800, so this is up high in the C1000 bank. Four. And we have a couple of results here. Oops, I typed that incorrectly. I did that in another video too. So around 2E100, we have some disk drive activity. Let's break this down here. So we're loading A with 15, loading X with 8, loading Y with 15, and going to FFBA, which is setting the file parameters. Logical number is 15, device number is 8, secondary address is 15. So this is your basic open 15, 8, 15. And then we're calling FFBD, which is file name parameters. We're calling FFBA, which is your file parameters again. So this would be if you were doing it in BASIC, it would be this, and this would be open 2, 8, 2. FFBD kernel routine is for the file name. A is the length of the file name, and X and Y point to the file name. So our file name is 2 characters long. That's C4 2E. Or I'm sorry, 2EC4.
and it's number 1. So we're opening 2, 8, 2, number 1, which is a buffer. And then we're calling ffc0 open file. Load X with 15, GSR ffc9. Define file as default output. Now that's important because we have a channel open to the disk drive under 15. So what's happening now is we're loading X with 0, we're loading 2EC6, X, and instead of printing to the screen as FFD2 normally would, we're printing it out to the disk drive channel 15. So let's see what's at 2EC6. Block execute, buffer 2, 0, track 17, sector 7. And then we are doing the same thing, defining the file default output and sending 2FD2 out to the drive channel, which is, 2ED2, memory read. Let's find out using Kevin Pickle's Disk Doctor. Kevin Pickle used to work for Electronic Arts. We're going to load a disk editor and we're going to go to track 17, sector 7 to see what is going on. This is information put on sector 7 that is being directly executed by the 1541 drive, not the 64. So what we can do is go into the monitor again, and you see we have the disk doctor on the screen along with the bytes. So what I'm going to do is just type disassemble, and what you're seeing here is what is on the sector as you see on the screen. Load Y with 255, increment Y so it becomes 0. Load 0412, Y exclusive OR, compare it. So we have a loop going on here. We're taking 0412, we're exclusive ORing it so it is encrypted, and we're putting it back. We're decrypting the code for as many bytes as there are in 4B0. And then here where you see garbage, this is where it would decrypt. It's decrypting this, so it's going to fall right through to the code when it's finished. I'm going to transfer this code from the screen memory up to C1000 in the computer memory, of course. I'm going to disassemble the code at C1000. And I'm going to alter this, so instead of using the drive memory, we're just going to use the RAM at C1000. So it's going to load the code from here, and it's going to decrypt it. I'm hoping it will work. We'll see what happens. Now the problem is it's going to try executing it. I'm not sure what's going to happen there, but alright, it worked. I don't understand much of this, to be honest with you. I'm thinking this might be for track 35. This would be something that Retro Leo would have to take a look at. I don't understand a lot of this drive code. But I do know that when you load the game, it goes up and checks track 35 and then 36. So I'm just going to give you a brief rundown of what we've done so far. Loaded the files in. one by one. Checked address at 2D, 2E. FFBA, FFBD, FFCF, these are all good candidates for disk drive activity, as you can see here. Found it in file, I believe it was file 4. Now, we're going to do a hard reset. I'm going to fill memory with stars, and if you've watched my other videos, the reason I do that is so I know exactly where the files start and end, because the file overwrites the stars. So looking here, this is area of memory that's not been touched. 0D00 is the start address. That's where the data begins. It overwrote the asterisks. And it ends at, for that we can just look at 2D and 2E, which is 69CO. So I've already made some notes here. Looked at the code in the game, found a block, executes track 17, sector 7, executes code in the 1541. And the save address is 0D100 to 69CO. Now what we're going to do is hunt for drive code, and we find some at 2E68. So what it is doing, after it's done executing that track and sector, it calls FFCF. FFCF is read a byte from the default input. So it goes through all the trouble of executing a sector, going up and reading track 36, calling FFCF, and this is the key line right here. This is what you want to pay attention to. Store DAD. If you look at DAC, we have load X with 0, transfer X to the stack. Okay. I'm going to run the game. I'm going to go into the monitor and go to DAC, and you can see how the bytes are load X with 255. If I load, let me do this again here. If I load 4 and I look at DAC, it's load X with 0. And if I call the drive routine, which is at 2E5D, so 11869, and then I go back and look at DAC, it's now an FF. So what the game is doing is it's checking track 36 and getting that byte FF and putting it there. Otherwise it takes a 0 and transfers it to the stack, and that just totally collapses the game. Just totally corrupts it. How do we crack it? Well, the first thing we can do is do a hunt from 0800 roughly to 8000 for where this drive routine starts. Since this is an RTS, we can assume that this is a separate routine, because it stops executing right here. Whatever it's doing here, it leaves, goes back when it hits RTS. So 2E5D, 5D, 2E, we have one right here at D42. Right here. This is where it calls the disk sector, gets that byte, puts it in DAD. The opcode is 20 for JSR, low byte, high byte, JSR, low byte, high byte. Change the 20 to an AD, and it becomes a load. It no longer executes that command, it just does a load. We can now save it from OD100 to 69CO. That's done. Now we go back into, I haven't saved that yet. Okay, so let's call it crack2. We're going to delete file 4 because we don't need it anymore. We're going to import the file that we just saved. Which is 4. If you use the Vice emulator, you can do this. You can type save. You can learn how to type first. I apparently don't know how. OD100 69CO. So the format is save, and then file name in quotes, device 8, start address, end address. That's how you do it in Vice. And it will save it right to your D64 file. So you don't have to go through the convoluted method that I am right here, importing it. I'm going to save it. And if everything works the way it should, we do a hard reset. We refresh, crack2. Let's see if it works. Looks good to me. So this is a little bit more tricky. If you were to do a file copy, the game would not work. If you did a disk copy, you would get track 17 sector 7, but you would have to make sure you got track 36 as well. So you'd have to use a special copier. That's why it's in G64 format. But now it's been cracked, and you know how to crack it, and you can do with it as you see fit. So this is Milosoft saying thank you for watching. Don't forget to like, comment, and subscribe.